We're here at Jamroll Bay, close to Takawaupa, about an hour's drive north of New Plymouth on the Taranaki coastline. This coastline is really significant in geological terms because exposed along this entire coastal section north of New Plymouth, we actually see a cross-section through the ancient continental slope and basin floor of this part of New Zealand as it was about 10 million years ago. Well, typically continental landmasses are surrounded by a zone of relatively shallow water with a kind of flat sea bottom that we call the shelf, the continental shelf. And at some point that'll roll over down into the continental slope where the seafloor steepens and deepens rapidly towards the abyssal plane of the ocean floor, or what we call the ocean basin floor. We're actually in a place right now where we have marine rocks, so rocks that were originally deposited in the ocean on an ancient continental slope. So we have mountainous or uplifted areas on the landscape being eroded off. Once sediment reaches the coast, there is a number of processes that can then move that material into deeper water. So for example, wave action, oceanic currents, and the sediment ends up being washed out and deposited on the shelf. As layers build up, as more sediment kind of piles on top, you often end up with an increasingly thick stack of this sediment. And just like a slope on land, gravity will act on that sediment mass. And we have these catastrophic events occasionally where part of the seafloor actually fails, just like an onshore landslide, and transports a huge volume of material into the deeper ocean in one kind of massive event. The rocks are intensely deformed, so something has happened to these rocks. So we know from studying this entire coastal kind of section that we are at the base of an ancient slope. So here we are at the Jamroll. So as we were talking about, these layers of rock that you can see almost rolled around each other were initially laid down horizontally, one on top of the other. One of the interesting things about the Jamroll is that we know that when these sediments were initially laid down, they were of course waterlogged and soft. But as more sediment stacked up on top of it, some of that water began to be squeezed out and the rocks start to become stronger. They start on their journey to becoming a solid rock. So we think that this deformation happened to the rock at a point when it was somewhere in the middle. It wasn't quite a solid rock, but it wasn't loose sediment anymore. So the grey layer, we can actually see tension cracks in the way that it's bent, as if it was actually had some strength to it. But then the alternating layers, the darker rock, when you get up close, you can see they're all squiggly like toothpaste, like they've been squirted into the gaps and into the corners. So these rock types, even though they were being tumbled down the slope together, have behaved quite differently. Okay, we're standing on top of the Jamroll now. And there's some really fascinating features that you can see on top of the structure as well. So this is really interesting. For example, what we've got is this small conical feature with a kind of round edifice at the top. It's kind of reminiscent of a volcano, and that's actually what it is. It's a sand volcano, which is a feature of what we call fluid escape. So sometimes when rocks and sediments are squeezed, a lot of pressure builds up lower down in the column. The fluid kind of almost erupts up through the layers of rock above where the pressure is building, and it carries with it particles, grains of rock, and kind of deposits them around the sides, just like a little volcanic cone, really. We can see this kind of long feature that's got these kind of furrows on it. And what we think this is what we call a trace fossil. So it was probably left by some little creature that was grubbing around in the mud on the sea floor at the time that this layer of rock was actually deposited. And of course, since then, we know that it's tumbled down the marine slope into the deep ocean as part of this avalanche. So we don't actually see the fossil of the little creature itself, but we see the trace of where it's been. So here we're looking at the sea stack just off to one side of the Jamroll. So you can see that we've got some more spectacular deformation in the rocks. And this is actually part of the avalanche. In fact, we don't see the base of the avalanche here at the beach. It's buried below beach level. So we have a relatively undeformed base to this sea stack, but then as you come up, you can see how there are more folds that have actually rolled the rock all the way around itself once again. And if you look closely, you can actually see a surface that appears to kind of chop the top off one of these folds. So what we're seeing is that within these avalanche events, you almost have a number of internal planes over which sections of the avalanche are kind of bulldozing over the top of each other and planing bits of the avalanche off of itself as it rolls downhill. Interesting little feature, you see what looks like a fold that's kind of been planed off along the top. It looks as if another kind of lobe of the avalanche has forced its way over the top, chopped the top off the fold, and the little bit that's caught in that triangular shaped little corner there is rucked up like a carpet. So one of the amazing things about this part of New Zealand is these rock formations that outcrop along the coast. Because of the kind of tectonic tilt of the continent, these rock units actually dip offshore. So we can actually go out to sea and acquire some marine geophysical surveys and actually image very similar rock formations beneath the seabed. And using that geophysical data, we can recognize further rock intervals like this that are highly deformed. And that kind of expands our kind of time frame over which we can examine things like this. We can examine these rock formations here in outcrop and actually touch the rock, and we can also trace them offshore beneath the seabed. This particular marine avalanche that we're looking at, we actually think extends about 7 kilometers along this part of the coast. The reason why we're particularly interested in events like this is that they really stand out in the rock record. So we've seen these lovely, well-behaved layers of rock, and then they're punctuated by these occasional but very dramatic mass avalanche events. And it acts almost as a signal. It's telling us something about what's going on in the kind of the bigger area. So is there been an increase in the amount of sediment coming into the system? May have caused too much sediment to build up on the slope and then collapse. Is it telling us that a lot of earthquakes are happening? They're shaking the slope and destabilizing the sediment. So they're giving us an indication that something bigger is going on. And that's part of the reason why we study them here in Taranaki.